Good morning, everybody. Hopefully you can hear me. Testing the audio here. All right, seems to work. So I don't have as much of a plan today as I did last time. I really just kind of want to dive in and play around with inverse semigroups for a bit. See how many people here have heard of them. Maybe build a little package for them. Right now I have them lying around inside of a code base that I have called Coda, but I don't really have them packaged up for reuse. So I'm thinking that that's my plan for the morning or afternoon. So I said last time that I thought it would be a short stream, and it wound up running almost 4 hours or about 4 hours. I will try not to make the same claim this time. But I do actually think it's going to be a short stream. Unless there's all sorts of pressure to keep going. So, let's see here. What is an inverse semigroup? Let me get a window set up to be the right size for this. Blow this up as big as we can and meaningfully write code. So, how many people here know what a group is? Let's start there. Hi, King. How you doing? Well, what I'm going to do here is we're going to start with the notion of a monoid, which is that we have mempty, append, with the, which we usually break down into, now we have semigroup, and so I can get rid of append. So semigroup gives us some funny little diamond combinator that looks like this, with the laws that it says it doesn't really matter where you put the parentheses. Monoid adds a couple of laws to that, which says that mempty acts as a unit for it. So for those of you who are less familiar, integers with addition, integers with multiplication, so addition with 0, multiplication with 1, each one of those acts as a perfectly valid monoid. Okay, and then mathematicians tend to like to go up and add, they like to move on to building up the notion of a group, where groups add inverses such that m appended with inverse of m is mempty, and inverse of m appended with m is mempty. But there's not really in the functional programming world, we tend not to say a lot about the space in between these two extremes. So there's, so I'm going to give a talk about these at Lambda World in a couple of months. So I thought I would dive into inverse semigroups to give some folks a little bit of a heads up on what other structures there are, and I don't know, just play around with them. I found them to be relatively useful recently, and they're very much underdocumented in the, well, they're not really part of the Haskell toolkit yet. So I'm going to kill these because these are provided for you by base now. In 8.4, semigroup is actually a superclass of monoid. Going forward, that'll be really convenient. So, There are other things kind of between monoid and group, though. So let's see what we can do that gets us, what fits into this space. So what if your inverses don't quite invert? So there's the notion of what I'll call a regular semigroup. We're not even going all the way up to monoid and group. We're going to go between semigroup and group. A regular semigroup is going to give us a notion of an inverse. So we'll move it down here, and every group will be a regular semigroup. Where now what we're going to say is that A appended with inverse of A appended with A is A, and inverse of A appended with inverse. So we're not saying we can get you back where you started. This doesn't necessarily become empty, which then appends into A. What we're saying now is, actually, I'm saying I have some audio clipping, so let me bring that down because people were complaining about it last time. What we're saying is that we get you back to some place where you could append back in an A and get back. So it's a little bit weaker. We don't even necessarily know that an inverse, a proper inverse, exists. If we did have a valid inverse, this would pass the test, right? We'd be able to just use A appended with its inverse is mempty, and then mempty appended with A is A, and so we'd get right back to where we started. But we might be able to do this without going all the way back to the start. And then there's going to be another notion between these two things that I'm going to want to talk about, the notion of what I'll call an inverse semigroup. And these are the standard mathematical terminologies. You can Wikipedia this stuff. And this adds that all idempotent elements of M are of the form M appended with inverse of M and that all idempotent elements commute. There's another way to talk about this, which is to say something about, is this an abelian semigroup? No, this is not an abelian semigroup. We do not have commutativity, and we do not need to distinguish right and left inverses because we've got, if n is of this form, then n is of this form as well, for some other element. These are not necessarily the same element. So we have that idempotent elements commute, but not every element commutes. So there's a subset of my elements that will be idempotent. So let's go look for an example. And the one that I kind of like, which is an example that goes all the way through to inverse semigroup, is to look at just systems of parentheses. Just give me a pile of parentheses and try and figure out what we can say about it. Well, if this is a balanced set of parentheses, then I should be able to delete any inward-facing pairs. And I'll be left with some number of parens facing outward in each direction. In this case, they all happen to face left. But I could wind up with some leftover unmatched parens facing out to the right as well. So we're going to invent something called the bicyclic semigroup, which is used to recognize something called the Dyke language, which is the notion of balanced parentheses. So here what we're going to do is all we need to know is how many parens we had facing outward. And I apologize for the fact that the camera is still bouncing. I have not had a chance to get that fixed since last show. So we need a semigroup for B, which will have B, C, D is, well, what is this? I have some number of A parens facing that way, B parens facing that way, C parens facing this way, D parens facing this way. And so if I had fewer B's than C's, then this is like A plus the C's minus the B's that canceled out. So excess C's overflowed and became A's. Otherwise, the excess b's overflowed and became d's. And the unit for this is going to be b00. I've used this as an example a couple of times. I think I live coded this for a talk I gave last year at Scala World. And so here what we're going to do is say that parsing of a paren is one opening paren. Parsing a closing paren is one opening paren. Yeah, a closing paren, opening paren. Parsing everything else doesn't change anything. And so we should be able to say parse char to b, and then check to see if something is balanced by fold mapping parse over x's and checking to see if that is b00. And balanced will take any foldable container that holds onto chars and give me back a result. Hopefully that works. I didn't actually check my code for sanity. All right, we have balanced parentheses checking. And we can check the obvious failure cases. Does that make sense so far? So what we've managed to do is parse parentheses completely in parallel. If we had a different foldable container that was like a tree, we could fold up over that thing together. In parallel, we could compute like a finger tree and store the result of having folded the finger tree so far. And so if you made small changes in the middle of your file, I can reparse in log time. Okay. So I have a grown-up version of this in the Coda code base, which lets you deal with things that are more than just parentheses and can handle brackets and braces and what have you. So now let's see what we would need for this to be a regular semigroup. This really can't be a group, right? No matter what you do, if I had some unmatched parens over here and I had some parens facing this way, no matter what I do over here, I can't get rid of these parens facing off to this way, to this direction. These two parens are completely inviolable no matter what I do on this side. And so there's no proper inverse. But I contend that there is an inverse that satisfies these conditions. Mempty equals undefined. Mempty is perfectly well defined. I have a mempty. I have a unit. I just don't have an inverse that gets me back to it. So do you have any suggestions for how we implement inv? I will let the Twitch chat join in. That's a wonderful suggestion, King. All right, BBA. So let's work it out logically. If I had some number of parens facing this way and some number of parens facing this way, and then I were to smash its inverse in, and then smash the original back in, what's going to happen is these and these are going to perfectly cancel out, and we get back to where we started. So A appended with its inverse, appended with A again, gets me back to A. Even though A appended with its inverse does not get me back to mempty. Right? So if I had some number of parens facing this way, and I append it with its inverse, I get So BAB appended with BBA is BAA. Okay. Now, what do we need for this to be an inverse semigroup? Well, I don't need to actually write any code. I just need to claim it. But what is the claim making? The claim, well, here we were saying that our idempotent elements were of the form something appended with its inverse. But something appended with its inverse here is just basically an integer number of parentheses facing outward. And then we should be able to figure out what's going to happen if I had b, let's say nn, appended with bmm for two different integers. If if n is less than m, less than or equal to, we can go back up to our original definition here. Place a and b with n. Yep. C and D with M. Well, what is this? We have n plus m minus n. This is just b m m, and this is b n n. So if n is less than or equal to m, we're going to go up to m. If otherwise, we're going to go to m. So this is max of the two integers that we have. So what we've done is the idempotent elements of this are a number of parentheses, and what we're doing is we're computing the max. So if you had two elements here and three elements here, I'm going to take two off of the larger, but then put them right back on. On the other hand, if I had two over here, I would take two off of the larger and put them right back on. So this is computing the max of these particular elements. We're looking for elements here that have some kind of nice shape. It's kind of like playing around in the game of life and finding gliders and stuff like that. They're not all of the structure, but they're some of the interesting structure. So here we have an inverse semigroup. And we found the integers with max as a knock-on consequence of this. I just think that's kind of gorgeous that pops out. And so all my idempotent elements do commute, basically, if all my idempotent elements are of this form. Another way to view this, there's another statement of this. I didn't actually say that, I didn't actually provide the proof that all idempotent elements of M are of the form M appended with inverse of M. That's a little more difficult. Another equivalent proof is to show that the definition of inv is unique. So this is the sort of standard phrasing here. So there, not quite standard phrasing. So when we start talking about regular semigroups, we start talking about whether something is a pseudo inverse of an element, because in regular semigroups, pseudo inverses are not unique. So really, maybe regular semigroup shouldn't be this class of give me the inverse of M, but rather is something an inverse. Which is a heck of a mouthful. Because we could have things that have multiple notions of pseudo-inverses. So let's see if I can come up with an example. All right. So what I would want here is to change these laws a bit. Is pseudo inverse of n is a pseudo inverse of m if n equals inverse of m. So these laws don't really work out so nicely now. I would need to know something like if B is a pseudo inverse of A, then A appended with B and B appended with that is that. I believe that's the right phrasing. We get something like this kind of pseudocode-y nonsense. Turning that into haddock-ish is probably about right. So if B is a pseudo-inverse of A, then we can go here and we can go here. I think that's right. I don't know if I actually get the second law. It's not particularly relevant. You can Google it. And then down here we have our notion of inverse, and I need to provide this inverse semigroup. I'll just provide it as a default. So now we have regular semigroup and we have inverses. Okay, and this stuff was me just proving that we got the integers with max as the idempotent elements of our inverse semigroup. All right, so we've got B as a regular semigroup. We're taking the default signature because we have an inverse semigroup for B. And I don't need the notion of group, but I'll put it there. Can I show my plugins in Vim? I actually don't know what I have installed in Vim right now. Let's see. Yeah, it's pretty minimal. I'm using Visual Bell so that I don't constantly ping. I have syntax highlighting on, and I don't use anything. Every once in a while, I'll go nuts and install a bunch of Vim extensions, and I'll move to a new machine, and I'll lose everything. So right now I'm using an incredibly minimal setup. All right, so we have closed. Okay, I wasn't sure if the maybe condition was right or not. So it looks like Snowman has hit Wikipedia for me, so I didn't have to. So the more Penrose conditions. Regular semigroups. Yeah, so the definition on Wikipedia is that a regular semigroup has every element is regular, which is that for each element A, there exists an element X, such that AXA equals A. So for every element, there is a pseudo inverse, and for every element, A has at least one inverse B, such that you can do on both sides. So the pseudo. So this is actually a little bit different than what I had said, so this is actually, I think, sort of the uncomfortable middle ground between what I said and what Snoyman had said, which is that because right now I had said before that there's a pseudo inverse which says that we have this, but I guess we would really want if B is inverse of A, then B is pseudo inverse of A, so that we've got this condition, but we also have this condition. All right. So we would need a I haven't actually coded this up in this style yet, so this is a fun little exercise for me at least. All right, so we've got the bicyclic semigroup is regular, which was the result that we demonstrated with B. B is the bicyclic semigroup. And then we want, there's all sorts of fun things for talking about uniqueness of inverses and stuff. So let's see if we can play a game there. So this is me kind of workshopping some material for a talk I'm going to give in a couple months. So let's see if I can figure out how to do this next one. I don't know if I can actually play video on here because I don't know if I get audio from the. So let's see if I can figure out how to do this next one. I don't know. Do I have audio from the Mac? Let's find out.
Oh, yeah, no. Oh, no.
All right, this might work. I'm going to have to rely on the fact that I'm just going to use my speakers and then play this so that I can hear it from the mic. So there's this quirk of Australian English that I was introduced to during my last visit down to the Queensland Functional Programming Lab, which is that in parts of Sydney and Brisbane, they're partial to actually speaking in this patter of it's not quite as bad as that particular parody bit, but it does generally have sort of a connotation that can be parsed by a native. We go to Urban Dictionary. There's entries for yeah, nah, and nah, yeah. So yeah, nah is like, yeah, I hear what you're saying, but no, you're wrong. And nah, yeah is I agree with your negative statement, but I'm going to give a positive. It's sort of the I didn't really agree with you, but now I do. So I was looking around for a, and I realize I apologize to any Australians in the audience or New Zealanders who are, I guess it's even more common, that for misappropriating your local linguistic quirks, I will get this wrong. So what we could do is we could define like a data type. Australian with constructors yeah, nah. And we could define like what is yeah, nah. Get some wiggle room here. So yeah, nah is nah. Yeah, yeah, yeah. Nah, yeah. Yeah. Nah. Nah. It's nah. So if we squint at it, it's just last. So this is like last bool. And so we know that this is using data.semigroups version of last. Hold on. Seeing how I got time. Novice self-taught programmer here. Okay. Making the jump from simple Haskell programs to actual useful tools. I will admit it probably took me a few months to actually get into the mode of writing useful Haskell. Mainly because there was a bit of an impedance mismatch from kind of switching from the sort of mathy bits of Haskell that are good for like Project Euler kind of problems and the like industrial strength kind of Haskell that Snoyman here likes, and which is taught through like real world Haskell. I don't know that how to put it. I don't know that you should necessarily be in such a hurry to make that jump back into practicality. Mainly because if you do, I think you in some ways you'll get right back into the grind of Haskell is like every other programming language, and I'm just going to sit here and write my CRUD apps in it. There are some tools that people have found that make things that are useful for just like getting crap done in Haskell. I think a large part of why lenses became popular is because they make writing those kind of hey, I need to write a CRUD app or manipulate crap out of a web page kind of applications a little bit easier to write. right? You have some kind of application state, and you need to wander into it and edit part of a record, or walk into maps inside of it, or go deeper into JSON bits and pieces that you're plumbing around from other APIs that you need to talk to. So in some ways, I think like learning how to use lenses and stuff like that is a good start towards like getting back into the practical. And I'm pretty sure Snowjerk here has by the way, is this Snowjerk or actual Snowman? I just remembered that Snowjerk is not Snowman. After, fair enough. We shall never know. Regardless, like using something like Yesod or Snap to randomly, put together web applications. Once you've got like Snap or Yesod or Servant or something under your belt, you can get a lot of practical stuff done in Haskell. So I would definitely focus on like you can keep on keeping on with like the theory side of Haskell until it wraps around and becomes practical. This was really how I went about it. I don't know that that's necessarily the best approach for everybody, but it worked for me. So, where were we? Oh, we were playing around with Australian English. So what I want to do is make a semigroup for Australian. Why do I use double arrow in my signatures instead of single arrow? So double arrow is for a... where do I use them here? I have a couple of them, like for foldable F and stuff like that. So these are constraints in Haskell. So this is saying that F can be any type so long as it satisfies this type class. So there's a type class of foldable things. So those give us methods like this fold map function. And when I'm defining classes, that's the notation that you use as well. On the Australian thing, what do I use? Do I have a double arrow in the... I don't think I have a double arrow. These are all single arrows. Australian is yeah or nah. It's not like they say anything else. Eek, show, ord, read, blah, blah, blah. Yeah, these are normal arrows. So what do we have here? Instance semigroup Australian, instance monoid, Australian. Well, here we break down. Last bool does not have a unit. There's no element that I could pick over here that consistently... I mean, yeah works on the left, but there's nothing I can put on the right. So we're not a monoid. Yeah, I think it is the resolution on your computer's a gazoo. So what is a viable notion of an inverse for our Australian? Well, we could pick inverse of yeah is nah. Inverse of nah is yeah. But I don't actually have inverse as a member of regular semigroup because I kind of demoted it all the way down to inverse semigroup. So let's see what we can get here. Yeah. Is yeah. I realize that doesn't sound sufficiently sarcastic to be legitimately Australian. Yeah, nah. Yeah is yeah. nah, nah, nah is nah, nah, yeah, nah is nah, under the last conditions. So what we have is we have two pseudo inverses here. Like, given yeah, I could sandwich either a yeah or a nah inside of it and get a yeah. On the other hand, so we also have two pseudo inverses for nah. So everything's a pseudo inverse. That I might. Inverse of and then what we have as a proper inverse is of yeah. But the thing is since our pseudo inverses are not unique, we don't actually have proper inverses in order to have an inverse semigroup. So, I started playing around with ways to clean this up. I thought this would be a fun little exercise, so let's see what we can do. So we can introduce sarcasm. If you've ever dealt with Tony Morris or most other Australians, I find generally that if they are constantly agreeing with you, they're really taking the piss. So yeah is nah. But this is not quite the exclusive ordinate monoid. We still have this bias in the nah yeah case. Because yeah, nah, and nah yeah are pretty well understood. I think we want we parse English left to right, so we want that. So that should be infix R. I can never remember. I want to shove it to the right. Yeah, that'll get us the structure of Australian English, and people can figure out Australian Hebrew and Australian what have you on another day. Sweet. So now we have a problem. This is actually not this is not going to be associative. Let's test that theory. First of all, let's just see if this file even compiles because it's been so long. 35 eq. I'm actually impressed that compiled. Yeah, nah. Yeah. Has become really sarcastic. So what happened? We grouped things up. The one in Fixel. Yeah, nah, yeah should be yeah. So we want this association. So we want in Fixel. All right. So now what we want to do is let's like go over yeah or not a yeah. I don't have enum. Enum bounded, and we should generally allow not a yeah. Yeah, that's why I wanted to fix it. It needed to be in Fixel. Otherwise, you get the wrong impression. We really want the last thing generally, but we want that little bit of sarcasm mixed in. So here we start running into a problem which is not a yeah, which should be that. Section must be closed in parentheses. Nah, yeah. There we go. We're gonna let everything be not a yeah, and then we'll go from XXX. What do I want to do here? I want to app these together and run a little test which says for each one of these things, let's first of all just give them back so we can make sure that we're doing something sensible. And what I want to test is A and here we're finding that this is not actually properly associative. So you would expect that. What is this? I think this is something like and not. Or not and. It's something like, x dot 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 y is something like not x and y. So that's not going to be associative. We've given up associativity. But if we just ignored the associativity issues, like kind of assuming we're always going to associate the infix L direction because it gives us the answer that we wanted, maybe we can fix it on the backswing. So what else could we do? So we've fixed one of the pseudo inverses, I think. Yeah. Nah. Yeah is yeah. 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 Is nah. Yeah is yeah. Nah. Nah. Yeah is nah. Yeah is yeah. Or nah. 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 Nah, yeah, nah is, what did we fix here? One of these should be fixed. Nah, yeah is, yeah, nah, I screwed this up somehow. What did I get? Nah, yeah. Or is this yeah, nah? One of these is wrong. So one of these two, I screwed up. So which direction should I be parenthesizing? I'm parenthesizing to the left, right? That's a nah, yeah, yeah. Okay, so that's correct. And this one is nah, yeah, becomes yeah, nah. Nah, nah, nah. I guess what I'm looking for is to say, what I really want is if somebody is constantly, and I was hoping that this was going to fix one of the two and then have to try and fix the other by appealing to nah, nah. If someone's constantly nah, 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 like really they're just in denial, and this should be yeah. But I've apparently made a flaw. So what do we screw up here? Yeah, nah is that's a nah, yeah, which is a yeah. Nah, nah is a nah. Nah, 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 yeah. nah, is yeah, nah, nah. What else we got? I apparently did not fix one of these things. All I did was ruin associativity. Okay. So let's add a little more self-denial and see what we get. Nah, nah is yeah. So now what do we get? Nah, nah, here becomes yeah, nah, still nah. Nah, yeah, nah. What did I screw up here? Nah, yeah is yeah. So yeah, nah is nah. Okay. But if we chose the other associativity, what do we get? So here we get yeah, yeah, which is nah. So this is a sort of the opposite of the colloquially Australian English. Yeah, nah, yeah becomes yeah, nah. Is nah. Nah, nah, nah. So the nah, nah becomes nah, yeah. Which is yeah. And nah, yeah, nah becomes nah, nah, which becomes yeah. Huh. So here we managed to find a thing that is like completely anti-associative in the sense that everything that like we agree one way is completely disagreed the other way. I was hoping that we could actually tease out a structure here where we would have a proper pseudo-inverse. But here we're getting the same answer on both of these, which is different than the result that I got the first time I looked at the problem. And I don't know what I did wrong. Huh. I'm glad I didn't do this in front of an audience of 4 times this size. So what do we have? Yeah, nah, yeah. I've lost my video on my screen. 1 second here. There we go. I have video back. All right. I was really hoping to get a nice... the naive version of Australian English does work as a regular semigroup. But once we start adding all the sarcasm to try and fix it, to figure out how do we make a monoid that can parse Australian English, I had assumed that I was going to be able to fix this by adding sarcasm and denial. But apparently even that is not enough to fix Australian English. All right. I will have to figure out if there is a fix and do it at a later date. But we do now have we at least have an example of something that is, if we go back to the earlier Australian English, before we started becoming quite so sarcastic. So we will naive Australian English. Will give us this thing. And here, everything works as a regular semigroup, but it does not work as a... there's no denotational semantics for Haskell, let alone Australian. So good luck with that one. Denotational semantics can be vastly overrated. All right. So we have an example of something that is a regular semigroup, but not an inverse semigroup. And we have an inverse semigroup. So why did I start thinking about inverse semigroups again? I started thinking about inverse semigroups again, partially because there was a paper linked on our Haskell by Brent Yorgi. this functional Perl on subtracting bijections, which made me think about partial bijections again. And in some ways, if you think about groups as being the sort of structure of bijections, like you can look at a group is in 1-1 correspondence with its the set of the automorphisms on it, right? So aught of G. Then there's a sort of fundamental inverse semigroup, which is to think about partial bijections. You have two sets, and you have a like for some subset of this is isomorphic to some subset of this. So this notion of partial bijections is sort of the thing that generates inverse semigroups. Okay, so we've spent a bunch of time like talking about them. We haven't really talked about where they come from or where you might want to play with them. So one of the ways to think about an inverse semigroup is to think about why are they weaker than groups, or what other things can be inverse semigroups that can't be groups. So we had our natural numbers with max, which were the thing that we got out of our just playing around with parentheses. We were playing around with bicyclic semigroup. We found that the idempotent elements all looked like integers with max. Well, integers with max, I could always choose an element to be its own pseudo-inverse. And then, because it's idempotent, aim appended with aim appended with A is A, so that's a perfectly legitimate choice. And so that would be a perfectly legitimate pseudo-inverse. Any other element less than or equal to A would work as a pseudo-inverse. But then inverse is the only choice would be A itself. So what are our examples here again? So we had regular semigroup. We started building I guess we could say regular semigroup for last bool. We had one. We could say instance max A given ord A, and yeah. What do we want here? We want the regular semigroup that we get on max A should let us compare them for equality. So we'll say is pseudo inverse of. So n is a pseudo inverse of m. N is less than or equal to m, and max n is the inverse of max m when n equals m. And here we actually can compute the thing. With the identity function. All right, so we now have another example of an inverse semigroup, and this one is interesting to me because it's not group-like. This is a semilattice. So in some ways, you can think of an inverse semigroup as sort of the least generalization of a group and a semilattice. You can have every semilattice. Like a joined semilattice, for instance, would be that I have, it's going to be idempotent. It's going to be commutative. So what did we need before? We needed that every element is if every element is its own inverse, then we can know that every element is of the form A appended its inverse, because this is just A, so that's trivial. So we can pass one of our tests to be an inverse semigroup, or we wrote the class for inverse semigroup. Did I kill the laws for inverse semigroup? We had them at some point. So the laws for inverse semigroup said something like A appended inverse A appended with A is A. Inverse of A appended with A appended with inverse of A is inverse of A. All idempotent elements are of the form A equals B appended with inverse of B, or A equals inverse of C appended with C for some other element, potentially, and all idempotent elements commute. So in the case of a joint semilattice, all elements are idempotent. And if our inverse is the identity and we are idempotent, then all elements are of this form, so that checks, and all elements commute, so all idempotent elements commute. So joint semilattices are inverse semigroups, just like groups are. So a group is a inverse semigroup with one idempotent element. The only idempotent element in it is the identity. A joint semilattice is an inverse semigroup where every element is idempotent. And inverse semigroups kind of cover this and the middle ground between those two extremes, where now you can have some of the elements are idempotent, which we saw with our bicyclic semigroup, where if we have the same number of parens on either side, now we have an idempotent element. So we might actually get fancy and say something like, how to do this. I would like to be able to say we could classify all of the elements in our inverse semigroup in a way that starts to feel category-like. So we could say, give me the type for the idempotent elements of M. Let's see if I can do this right. And I'm gonna want some extra conditions. The idempotent elements of M should be isomorphic to the idempotent elements of the idempotent elements of M. This will let me actually capture in types that we want to talk about the natural numbers with max. And I would like inverse semigroup for idempotent of M. So now we have a problem. We have a potentially infinite seeming tower of superclasses. But fortunately, a couple of years ago, I managed to talk Simon into giving me a language extension, which made me very, very happy. Undecidable superclasses, which iterates this until it hits a fixed point or spins forever at compile time. And so we have this ability to build an idempotent. And what I wanted is I want a couple of combinators that let me, first of all, figure out how to take M and get me, or given an idempotent for M, build the M for that thing. And we can build, given an N, it turns out that these should exist. And this is going to start feeling a lot like a category. So for our inverse semigroup for the bicyclic semigroup, our idempotents should be I used int rather than integer because or naturals because I'm lazy. The identity for max n is bnn. The source of BAB is going to be A. The target of BAB is going to be B. Oh, wrapped in max. And let's see if we've got enough structure here to do what I want to do. We've got an inverse semigroup. We have identities on this. And we could default this stuff. By default, idempotent of m will be just m. And whenever the idempotent of m is m, then we will fill in identity equals really identity. And in that case, again, default for the source. The source mapping will be the identity and the default target mapping. All right. So idempotent zero. All idempotent elements commute. Okay, so if we are an idempotent element, the source and the target should be the same, identities, etc. Do I have Discord up? I apparently am not hearing anything on the audio from Discord, so I apologize if anybody else is asking questions over there. I'm not hearing audio on Discord. I apologize. So if somebody wants to throw a question on one of the chats, in like the text chat, what is idempotent m, twiddle m? What does the twiddle mean? So I'm saying that those must be the same type. If the type of idempotent m is the same as m, then we can carry on with it. So what do we have? We have source and target. Starting to actually come together. M appended with inverse of m. We're all good with that. This should actually require inverse semigroup for every group. The idempotence for a group will just be unit. So let's take an example of a group. Yes, inverse semigroup and monoid. What do we want for our group structure? So the default for IDD for a group will take, I guess, unit to source for a group is going to be what? It's going to be an element of the idempotent set, and the only one we have is empty. Target for our group is also going to be empty. This is really boring. So in the group case, these are not terribly interesting. And I just figured out why I wasn't seeing anything in the chat. I was scrolled back. Max int needs a semigroup instance. I would believe that. Max, no, here we go. We've got it. I just need to fill in the extra stuff, but that should fill in by default. So hopefully inverse semigroup for B should fill in with undecidable super classes with a capital C. It's probably going to need a whole soup of other extensions. Import data.semigroup max. All right, so that type checked. What directory am I in? Inverses. Where I jump? I'm probably jumping up and down my camera because I have I ordered an arm and it hasn't shown up to hold the camera in a more stable position. But right now it's on a desk that's pretty wobbly because I moved it around to try and stream better. But as a consequence of that, the arm that I had for that is currently sitting over here, so I can have one for like sketching and stuff. So I can flip into this other, here's my drawing mode, and you can see me scribble. Unfortunately, that meant that my other camera has been sitting rickettily on the back of a laptop. So sorry, Steve. All right. So what do we have so far? So we now have regular semigroups. We have this notion of an inverse semigroup. What I might want to do is build... so what we're starting to get here is this is starting to feel like a category. I've got an identity. I've got a notion of a source. I've got a notion of a target. If we look at it, if we take A and append it with source of A, then I want to get A, or append it with target of A. And if I take source of A and append it with A, I should get A as well. And so this sort of suggests one way to get source and target is to actually take A and append it with inverse of A. And this suggests that A appended with inverse of A appended with A. So this is like M appended with inverse of M. And inverse of M appended with M. But this would require this requires idempotent of M to be the same as M, and so that works. So what we have here is sort of a category in disguise. But what are our arrows or what are our objects? And so one way to do this is to maybe build up the notion of a partial semigroup. Or a partial we can build a partial monoid. And then you would have the arrows that compose would be the objects that compose would actually be the arrows. And then the fact that it sometimes can't compose would be like we've taken a bag of arrows, we kind of forgotten where their objects were, and we allowed the ones that connected head to tail to actually connect. So that's one way to actually model the partial semigroup of how our elements connect. But I'm not sure that actually adds a whole lot of value. I do have a use case that actually needs that much structure. I wrote it as part of my little Coda project. Actually, I wrote it to answer a comment from, I think it was Alan Zimmerman on the Coda IRC channel on Flipcode. Or not on Flipcode, on Freenode. And it was, how to put it? He was interested in for the Haskell IDE engine, which acts as a Visual Studio Code plugin, mapping old source locations to new source locations and back. And if you look at this as a partial bijection between old source locations and new source locations, you could almost just model it as like A to maybe B, or int to maybe int, and an int to maybe int coming back. And that would work just fine. But it's going to be really inefficient. And so the goal was to be able to reuse old error message positions and old type positions as you've typed into your program, and then map the current locations back to the old positions, and map old positions forward to current positions when you're showing things. What is Coda? Coda is a little pet programming project of mine. It serves a bunch of use cases. I'll be talking a little bit more about it in the future. Mainly, it's sort of the intersection of three different problems that I want to work on, and some subset of those problems will come out. At the front end, I started playing around with all sorts of crazy parsing technology, which was actually where I first discovered all this inverse semigroup stuff. That and from talking to Unitl from Reddit on down in New York, and so that was where I first found uses for inverse semigroups. And then later on, I found more of them playing around with other stuff. But at the parsing level, I've got that problem. At the type checking problem, I'm looking for a language that's better at type classes than Haskell is. That's a whole other can of worms and would subsume this entire stream if we started talking about it. And then at a runtime level, I'm still interested in doing SPMD on SIMD evaluation for functional languages. And so those are the three major problems that I've been chewing on. The parsing one, I've lost a lot of interest in it. It's not my critical path right now. Not Idris. This is Coda. Idris is another let's build a dependently typed programming language project. But for various reasons, I don't find myself compelled to write an Idris. And again, I don't really want to derail myself for the entire stream. So what do we have? We have regular semigroups. We have inverse semigroups. Oh yeah. So the problem that Alan had was mapping old file positions to new file positions and back. It turns out you can actually come up with a nice partial bijection between these two things, which implies that there is some inverse semigroup lying around. And that was one of the sort of bigger uses of all of this machinery that I was able to come up with. The other use case that I had for this was well, in the parsing of code for Coda, which is like, let's say I'm trying to parse all of my input, as much of my input as I can monoidally, so I can do parallel parsing of chunks of my source file, and that way, if I make small changes, I should be able to roughly reparse in polylog-ish time. Was my goal. And we can see that I can handle the parenthesis structure easily. And it also turns out that if we make a couple of modifications to the rules of layout, that you can parse layout monoidally as well. And so there was a talk I gave at Scala World on monoidal parsing. I will just dump the link into the chat, so if people are interested in watching it, they can. And so dig into that one later if you're curious about more of this stuff, at least on the parsing angle. But one of the problems that keeps coming up there is that there's this there's something called a semi-direct product of a group and a group and a joined semilattice, which turns out to be very, very useful to me. And so those things tend to be inverse semigroups. And I have yet to come up with a use for the inverse semigroup part of that, but the fact that they are is somewhat telling to me. So that's where a lot of this stuff kind of came from. So I don't know that I actually find value yet in any of this. Like, let's track the idempotence as a separate type. Let's expose this sort of almost category-like structure where we have the mappings from our idempotents act like our objects. Our arrows between them will be elements that have those things as source and target. Or rather, they're anything such that if you were to append the source on one side and the target on the other, that you don't change the answer. So there's a category of associated with any individual inverse semigroup, where we can say our objects are the idempotents of our inverse semigroup, and our arrows are anything such that if I were to append that element on the idempotent on the left or on the right, it leaves the arrow unchanged, or the element that is our arrow unchanged. So like for our parentheses and stuff like that, so if I had my objects are things like, say I have 1 on the right-hand side and 3 on the left. Any element here, that any thing in the middle that has at least 3 parens and at least 1 paren on the right, when subjected to these changes, comes back out as directly as it was originally written. So this would be an example of an arrow between, this is 3 and 1, and this is B5, 1, would be a perfectly legitimate arrow, drawing kind of a arrow with B5, 1 in the middle, between 3 and 1. And then the arrow, the identity arrow here, supposed to be me drawing an arrowhead that is looping. Is B1, 1. And the identity arrow here is just B3, 3. So B1, 1, is our identity on that side. B33 is our identity on that side. If we append B11 with itself, we get B11. So it acts locally like a unit. B33 kind of acts locally like a unit here. And if we look at any of the endomorphisms from this thing to itself, this acts as a unit for any of those. And we can append them together. And so we get a monoid locally. And yeah. So there's all of this weird structure that we can get out of just playing around with these, this sort of very weak generalization of a group. Here's a group where we now have inverses. Inverses are unique, but they don't fully invert. And I don't know. I find it incredibly interesting that A, that there's really nothing that tries to talk about this in Haskell, but B, that they're actually kind of I don't know. There's so much structure to them. Another example here would be to build. Let's go build that semi-direct product that we were talking about. So for that, I'm going to need the notion of a monoid action. And so this is why one of the reasons why this stuff doesn't get packaged up so nicely in Haskell. And so like last stream, I spent a bunch of time agonizing over how to build an API for authenticated computation, and we went through like 4 or 5 different designs. And this time we're going to see another problem with like trying to do this in full generality, which is that even just talking about the notion of a monoid action for some M on some set S, this is going to be something like act M on S. Like we would like M to determine S or S to determine M, and neither one of those is compelling. And so you wind up with a great deal of overlap if you start trying to use the unbiased version, but you wind up with lies if you try and pick one of the biased versions of the other, because there's like choices of I can take instance monoid M or endo of M acts on M, but also I can take M and where or endo S. But so they're here. M is determining S, but I might also want to have things where S determines M, and so this becomes a complete mess where neither one can determine the other one in full generality, and it just becomes a sewer of new types in order to try and work with this thing unbiased. In the Coda code base, what I do is I fix M, and then I curry it out to the module signature. So I use backpack in order to pick M. And so then I just build a class like relative S, and I lock this down to be some monoid, which I call delta. But if we just talk about it as if we had this monoid action class and that it was nice, maybe we can get by. So what is a monoid action? A monoid action says that if I act with mempty, I'm going to, I know that, first of all, I know that M is a monoid. Action of mempty is the identity function. And the active M appended with active N, or composed with active N, is active the appended elements. And we could come up with a notion of a semigroup action, which would be the same thing minus the mempty law. Group actions, you can guess. Basically, you just have a monoid action because everything you need to be a group action just follows from being a group and being a monoid action. But then we might need the notion of a... So there's other notions here. I might want to have a monoid that acts on a group. And so that's this notion of a... Call it a monoid action. M acts on N. N is also a monoid. This would actually be a distributive and Unitl action in distributive Unitl action. And so here what we want to say is that if we act on with some G on M, we append that with, or I need names for these things. Act with M on A and act on M on B. This is the same as if I were to act with M on AIM appended with B. And here, if we act with M on mempty, this is mempty. This is the distributive law. This is our Unitl law. So I apologize again for the bouncing up and down that I'm doing in the corner there. My camera is really wobbly. So given one of these things, we can actually find something that is more interesting than a product of two monoids. So we have this type in, like, we have this thing lying around in Haskell: monoid M, monoid N, monoid MN. And here we know that mempty is the pair of mempty and mempty, right? And appending we could make this notion of what we'll call a semi-direct product of M and N, which still has two data constructors. But has a stronger condition. So we need a distributive Unitl action of M on N. Implies that we have a semigroup for semi-MN. Yeah, check, sir. I don't know if I'm actually going to package this up. As we're going, this is becoming messier and more specialized, and we're starting to see that, like, this monoid action stuff really doesn't package well. So I don't know if this is going to turn into a full library. I just kind of wanted to start exploring the space in public rather than just have it be in a private repo somewhere that I have. So here, what I want to do is, instead of just mashing things together independently with, semi-MN just like we did up here. Let's mangle this a little bit. So what I want to do is I want to act on D with A first. And that's not immediately obvious that this is sound. So what is this? Like, where might you use this sort of thing? Let's consider sets with integers. And we're going to use our monoid action is going to be integers acting on the set by adding to every element in the set. Okay. This is it's a perfectly legitimate action. If we act with 0 on a set, we leave the set unchanged. If we were to add the integers and we were to act in sequence, this is going to act appropriately. So it's a perfectly legitimate monoid action to take every element in a set and, like, add n to it, where n is the integers that we're offsetting by, and where 0 acts as our unit. Then it's a distributive Unitl action, because what I could do is if I had some number that I wanted to add to this set, and I wanted to add the same number to this set, I could add the number to the sets individually and then merge them, or I could merge the two sets and then add, and I would get the same set. Similarly, if I act on the empty set, I still have the empty set. So this is the notion of what I've called a distributive Unitl action. We've seen one example, which is integers acting on sets of integers. And so now what I want to do is let's look at like the semi-direct product of those integers. So what would that be? This would be something like instance monoid action. This is why I don't want to write this code for real, but we would have some kind of monoid action of sum of int acting on set of int we'll just add or offset. And then this is a distributive Unitl action. Again, I would not package this way, and I really want to make sure that that's clear before someone runs off and tries to do so. Since we're there we go. Just to shut the compiler up so that GHCID is happy. So now we have a distributive Unitl action that can work on our sets. So now we could have now we can look at something like the semi-direct product of integers acting on a set of integers. So what do we have here? Now what we have is we have like a such a semi would look like I have a over the range of 4, I have the set from list 0 to 1, 2, and 3, or 0 and 2. And then if I were to mash this together with a semi sum 4, and I had the from list of I don't know, 2 and 3. What this is saying is what we should do is we should, if I had like the interval over which this set was taken from or something like that, and another interval, and I wanted to compute like the disjoint merge of these two sets, what I'll do is I'll shift everything in the right-hand set over by however long the window is, and then glue the things together. So like if these were like mappings from like source locations within this interval, and these are source locations within this interval, and I want to like glue the sources together, I really want to have a longer source interval, like now it's 7 characters long, and these things should be zero and 2 should be left alone, but now these should be like 5 and 6 because these should have the 3 from the first thing prepended into their position. This is different than what you would get with the direct product, where the direct product would just mash this together into 0, 2, and 3. So what? So I start using this when I start playing around with like parsing, because I might want to be able to say, hey, look, here is the a set of source locations or intervals of my source file of where different names occurred. And here's the mapping for this side, and here's the mapping for this side. Now let's like shift this one over to its appropriate position, and then glue the results together. So now we have a use case, at least with this, like these notion of like distributive Unitl actions, and I should be able to actually find that notion of a. Yeah, distributive Unitl actions. I'm not finding the. So here we're finding unitary acts and transforms. Distributive. Anyways, there is a notion of an action of a monoid on a semigroup. But I will not be able to usefully find it very quickly live in front of an audience, so I'm going to leave that alone. So again, in practice, I kind of like the approach that Coda has taken here, where what I did was I curried out the choice of M to build a class that was just the monoid, the actions of a particular monoid on a given data type, and then I was able to write a lot of code that cared about that. So if I go over and look at the Coda code base here, we can actually see this in practice. Coda, all right, let's go to lib. Coda common, Coda algebra, no, not algebra, Coda, where's delta? Coda relative, delta type. So here I have a single monoid, let's call it delta, which is just the integers with addition. It has a pile of instances. And then what I did was I have this Coda group relative backpack library. And in here, what I have is everything is abstractly implemented over some signature for some data type called delta. And then I have a bunch of containers and things like that that work against that signature. So the signature for delta, delta will be some monoid that has a pile of instances. In my case, I'm using num to horribly approximate a group. And so if we go back to our current code base, let's get rid of monoid action and replace it with this notion of relative. We're only going to obsess about one particular choice of delta, which would be eq show num instance semigroup and the monoid for delta will be mempty is 0. Since we derived num, I can use plus and 0 directly on the type without having to put on and take off new type wrappers. So now what we have is relative. S is just saying that, and a sort of be clear that we're talking about a special case. I'm just going to replace act with rel. So we relocate by delta some data type S. Now we can just talk about like sets of deltas maybe. I'll just do this as rel. So this is set of any type A such that A is relative, but this is a lie because we need more. This is true. These are true. These are the things I want. But now these are distributive Unitl actions. Call this a relative monoid. And so this is a lie, which I'll have to fix in a second. But now we can come down here and we can lock this to be, I have some delta that is going to act on n. And here we have a semigroup. So again, we've locked delta in place. We just said, hey, delta is some monoid. In my case, I would normally build this as a backpack module signature or something like that, and then pull delta out into that signature. Now we have a class that is peculiar to the choice of monoid. So I can't abstract over the monoid, but I don't have to fight with multi-parameter type classes without like proxies or something like that picking out the instance. I don't have to fight with instances that would overlap other instances where the choice of like endo S always works on S and stuff like that. That kind of stuff would cause overlap between these two sides. But for right now, everything's in one file, so I can just lock everything down to this particular choice of monoid 132. So why is this a lie? What we really need here is we need to know more about the behavior of rel. So what we don't know is that if I were to relocate, if A is less than or equal to B, I want that relocation by some m of A should be less than or equal to relocation by m of B. Not only that, I really want the stronger condition that if A is strictly less than or equal to B, then relocation by m of A is strictly less than relocation by m of B. So I want this strict this notion of like a relative strict order, relative A ordered A with this extra law. That if A is less than B, then relocating A preserves this relative ordering. And that means I can relocate the keys in my set. Then we can have things like relative A or strict relative order A. And here, like, rel is a mess, right? Because we would have to go through and, like, naively right now, with all the tools we have, we would need to deconstruct our map. And then we should take the keys and values, and what are we going to do with it? We're going to take our keys, and we're going to relocate by n our keys, relocate by n our values. And then build a map from that list. So we could do something like rel n and rel n, or and build a really expensive version of this. But this is embarrassingly slow. Semi-n. Instance num, generalized new type deriving. What else I mess up? Could not match expected type map kv something. Convert the map to a list. Relocate. Instance relative monoid set int 152. Where was that? All right. So now we fix semi. So we have now the notion of semi-direct product of some delta and some data type. And we've got a really, really horribly slow way to map over maps and sets, which require us to touch everything in them. To kind of revisit the material from that talk that I linked earlier, one of the things that we can do is we can try and build, like, it's always possible for us to say, hey, look, if I have a relative A, then I can take a delta and an F full of A's for any functor. And F map relocation over it. And so any functor can be made relative. It's not necessarily the most efficient way to make it relative. So let's make containers that are relative, or let's look at, like, if I were to want to relocate a list of things, that's going to take time proportional to the length of the list. And that's really galling if my original goal for all of this stuff was to use it in parsing, where I might want to give you a list of errors or something like that, which could be linear in the length of the program. And now I would be completely hosed in terms of the amount of time that it would take to relocate that list. So we need to build a more efficient notion of a list that can be relocated. So one way to do this would be to hack up our notion of a list. Instead of having const A, list A, or nil, or let's put nil first to kind of match up with the way that it's ordered in GHC. Here where we're deriving, I don't want to do any deriving actually. What I want to do is shove a delta in each one of the const cells, so that relocating by delta mangles the outermost const cell. Relocation by 0 of anything is the original thing. Get a little bit of sharing. Relocation by delta nil. But relocation by delta of const delta prime AAs is const of the glued together deltas. And what we've done is we've moved the costs around a little bit. We can unconst from this thing. We can take A to maybe A and list of A, or sorry, list of A to, and unconsting from nil will be nothing. And unconsting from const DAAs is going to be just relocate by delta A, then relocate by delta the tail. So what we've done is we've moved the cost to the time of inspection. The inspection was going to pay 01 to visit that element anyways. And if relocation is 01, then we've paid 2 01 costs at that time, instead of one big linear cost in the length of the list to relocate ahead of time. So now I can relocate my lists in 01 time. And what's kind of cool about this is that I could report that list of errors and then relocate that list of errors. Say that list of errors, they have a finger tree worth of source text, and I can monoidally parse somehow. When I start down at the leaves, I'm going to start with positions that are relative to the source chunk that I've got. And as I'm walking my way up the tree, we're repositioning and walking up higher using this notion of a semi-direct product to kind of push the positions around as we want them. So we could have like an error is a message that occurs at some position. And to get a little bit more sharing, we'll add that. And now that we have this notion of error, we can talk about a list of errors that can be relocated cheaply. The problem with lists here is that appending lists is not fast enough. So you want to start building a container that has O1 append, but still access to O1 to the head. And fortunately, Chris Okazaki can come to our rescue with his book on purely functional data structures. For those of you who are not familiar, there's this book on purely functional data structures by Chris Okazaki. If you're interested at all about how to reason about asymptotic performance of code in Haskell, this is the textbook, or even in just pure functional languages in general. This book is a wonderful guide for why you might need to care about laziness, if you care about asymptotic performance at all, and you want functional code. In particular, it spends a lot of time breaking down the traditional notion of how to do amortization in a world where all of the previous versions of your data structure are still around. Because in a functional programming universe, right, you have access to all of the previous versions of a data structure. They're still there. Everything is persistent. And so you can't just use a bunch of cheap operations to pay for, to earn credit towards a big expensive operation, if you could always go back to the step right before you did the big expensive operation and make you do the big expensive operation all over again. So there's this notion of ephemeral versus persistently amortized performance that becomes really important once you start moving into this functional programming world. And he sits down, like phrases the problem, and then like more or less solves it dead in one book. So if you're at all interested in asymptotic performance, I highly recommend reading Chris Okasaki's book. Then if you Google for what's new since Chris Okasaki, I think there's a nice answer from Jim Apple on Stack Overflow that kind of talks about newer data structures and stuff like that have come out since. And I've given a couple of talks on this topic. So that's a link to the Amazon thing. For those of you who don't want to throw money at the problem, there is a version of this from his thesis, which is available online. It is slightly less thorough than the book. It's missing a few examples. And it doesn't have the Haskell appendix that makes it so easy to transcode everything into Haskell. The IMC3LL. So what is the follow-up for regarding data structures? So there's the book that I was mentioning from Chris Okasaki that I gave two links here. One is the one to Amazon and one is here. And so what I want to use that for is to build a data structure that has O1 append, but still lets me relocate in O1 time. So I want to modify this. So what he builds is he builds a number of queues. And just at the risk of kind of skipping to a punchline, one of them looks kind of like this. I have a queue of things like this is the stuff I'm pulling off. This is the reversed version of stuff I'm going to put on there. And then here's a thing to fully de-amortize the cost of it, which has to be worked with very carefully. And then what I can do is I can append. I can't append here, but it gives me a notion of a queue. And then I can build a notion of a catenable queue, which is built out of, like, it's either empty or it's I have an A and a queue of catenable A's that are not empty. And so here, if I had the ability to relocate these queues in O1 time, then I could work smarter and build a catenable list that can be relocated in O1 time. So that's sort of where I was appealing to Okasaki. He goes through the construction of this queue in detail. But for that, I kind of want to make a couple of tweaks to the way I'm working with my list here, because this is still annoying. I have to put this delta and unpack it in every data constructor. Every data constructor in my list got bigger. Another version of a list would be to say, hey, look, I've got a list data constructor. I'm going to put one delta on the whole list. Just call this L for right now. And here we could say something like we're relative. Oh, and I would like to build a monoid for this list here, which was the original problem. Monoid for list of A, which required me to have mempty is nil, and the semigroup for this original list of A looked like what? It looked like I need to build up the delta that I'm going to apply to the tail, or I need to work relative as I go. There's a couple of options here. So, I don't know, to go starting from 0, now go const d AAs is const d A go or d prime. What is this? Is const d prime left alone. Now we're going to keep going until we d plus d prime or d appended with d prime. I want to be careful about that because I haven't needed anything with inverses yet. On A's, B's, and then go D nil B's is going to be relocate by delta B's. So we eat up the left-hand list until we're done, but we pick up accumulated deltas, and we apply the delta to the second list. This would be how we would do a semigroup for a list. Monoid has nil, but this is still linear time in the left-hand list length. Even though relocation is cheap, accumulating the delta that I'm going to apply to everything later is not. So here's another version of it, which has the same problems, but which moves the cost around a little bit further. So here we want, and here we could say something like instance relative monoid list A. So this was saying that we had, if I were to relocate a list and then relocate another list and then append them, I would get the same answer as if I were to append and then relocate. So now this is an alternate way to build this notion of a list, where what we'll do is we'll have a single delta. And in this case, we're going to have in order to const onto our list, we have to be more careful. And so here's the problem, which is that I have a single delta that's going to be sitting out in front of my list, but if I go to put this element into this tail, it's going to be mangled by this delta when I go to unconst. So when if I write unconst for this thing, we'll take a list of A, and we'll give you maybe an A and a list of A's for the tails. So here we're going to take list for some delta. Empty list is going to be nothing. List for some delta A const onto A's is going to be just relocate by delta A, and then we're going to put the L data constructor back onto A's instead of relocating. This is one notion of a list that we built. Rather than clobber the same names, I'll just build a data type for L, const of A onto L DAs. This one's interesting because now we want to put this A, but it's going to get mangled by this delta if we just did this naively. Delta is going to mangle A. So what I want to do is relocate by like the inverse of delta A before I put it in. Why? Because then when I go to pull it out, it's going to have delta applied to it. So inverse of delta appended with delta is going to get me back to unit as long as delta is a group. So here we need a real group. We can't just get away with like an inverse semigroup. And with that actual group structure, we can use L instead of list, having one delta that we share over the entire list. And it's pretty straightforward to implement the semigroup for L. But now we actually need relative at the time we go to instantiate the semigroup. From appending these things, instance relative gives me a monoid for LA. I'll leave this as an exercise. This is also an exercise. And then we can come down to our notion of a queue, and it becomes really obvious that if we were to do the same thing for L that we did for L to our queues, we could pull a delta out in front of this thing and have every one of these things just share a single delta. So we could build relocatable queues in the sense of Okazaki. Hi, Max. We're writing in Haskell, and we're playing around with the notion that is found in abstract algebra of something called an inverse semigroup. And at the moment, we're off playing around with monoid actions and actions of monoids on monoids. And the reason this stuff is all useful for parsing, it turns out. But the problem that we're currently trying to tackle is like how do you like parse things in parallel and glue the answers together without paying full price for everything all the time. So we're pretty far down in the weeds, I'll admit. So if you've never seen Haskell before, this might be you're definitely jumping into the deep end. But if you want to just get a sense of how a Haskeller works, this might be a good stream. So what we have here is now we can build this notion of a queue where we can just relocate our queue using the same machinery that we had for L. Like the nice thing about L was instance of relative for L of A was kind of obvious, right? Relocate by delta L delta prime A's is just glue that together. I mean, one of the reasons why I was using num earlier was just because it's kind of nice, a little bit easier to just say relocate by minus D if I know that, if I didn't want to build a group class and manipulate it. Because delta has a num instance lying around, I can just use it. So I want it to be a little bit sloppy. I can just do that. And that lets me do things like D plus D prime, which is a little bit shorter. Again, very sloppy. If you disallow nested comments, could this parsing technique be applied to Pascal? That was sort of what I said in the previous talk. So in that talk, what I did was I made one change to the rules of layout, and the other change was to remove nested comments. And that the removing nested comments was to allow me to use a Dyke language parser to recognize comments. That lets me use like the parser that I was fiddling around with for parentheses at the beginning of the beginning of the talk, to recognize Haskell comments. And then I can recognize Haskell style layout also minutely. And so that much stuff can then be applied to a Haskell-like language. I wouldn't necessarily go so far as to say I can apply it to Haskell, because Haskell has some rather annoying rules with regards to layout. Do I have a link to the talk? There was a link given earlier. Let me... And Y Sancock seems to have found it. All right. So basically the idea was that once we've applied this trick to delta, exploiting the fact that delta is a group, what I can do is I can do the same thing to Okazaki's notions of queue. I don't remember which queue this one was. I think it's his real-time queue. This is the one that has the correct worst case behavior instead of just the correct amortized behavior. And then what I can do is I can relocate catenable lists of things as well. So I didn't build all the excess stuff for relative, but it's pretty easy to see that for these... that one's pretty obvious to see, probably with the same caveat as before of relocating by 0 should leave the data constructor intact. And then you can build, obviously, a relative for catenable lists of A. So relocate by delta catenable thing is catenable, relocate by anything empty is empty, relocate by delta catenable A or CA is C of rel dA. And this version would require me to have a relative A. So as long as A's can be relocated in constant time, then this can be relocated in constant time because my Q can be relocated in constant time and my A can be relocated. And so this gives you the ability to borrow all of the power of like Okasaki's book, just like revamped a little bit. So I can have them be monodally relocated, or like relocated by some kind of monoid in constant time, and still have constant time append. So we've had to go off and like dive through some pretty obscure data structures to get here. But with this, we can do the same kind of construct that we did with where we shoved deltas in every one of our data constructors. And we could go through and build this helps exploit why this is the Coda group relative package. This is like, let's build that queue that we just talked about. My queues have, here's the delta, here's the 3 lists, here's all the other operations that I did not implement just now. We can build catenable lists out of empty elements, or here's a catenable A catenated onto a queue of non-empty catenable lists. All of the logic to make all of that stuff go is in Okasaki's book. This is implementing cons and uncons in a like lens compatible style, so that you can just use the cons and uncons functions that lens exports, which are more polymorphic. And the end result is you now have catenable lists of errors. But we talked earlier about like building maps, where we needed that strict relative order on our keys. So what I do here is I take the code from data.map, I shove a delta in every one of the data constructors, just like I did with the lists, and a relocated tip is just a tip, a relocation by 0 is just the element, and relocation by some delta of some binary constructor works. And this works so long as I have a strict relative order on my keys. This project is on GitHub. GitHub, you commit Coda. I'll dump it in chat. And yes, there are vulnerabilities in the JavaScripty bits because I have JavaScript in there. So the particular bits that I'm looking at are in the Coda lib folder, and then we're in Coda group relative. And yes, this is definitely a cooking show. Or this portion of it is definitely a cooking show. We don't have all the inverse semigroup stuff in this library. So all the first hour and a half worth of the stream was actually like we were actually cooking it. So here I have queues, and one of the nice things here is this is of course being recorded, so you'll be able to watch this later if you're having trouble following along perfectly in real time. So what I was starting to explore was, let's just take the code for data.map and shove deltas in all the data constructors. And you could do this for an arbitrary monoid that is going to be your delta, that you want to have act on your keys and on your values, so long as if you were to relocate your keys, the keys wouldn't swap order. Right? Like if I were to relocate a map with these keys, like the keys should stay in the same relative order to each other. That way, like my keys could be positions, or they could be values that don't care about positions at all. They could just be names or something. It's perfectly legitimate to relocate a name and then just not do anything to it. And so now we can have a map where my keys and values can have positions involved in their contents, and we can work with. Yeah, so ProFunctorBot is maintained by Brian McKenna, and yes, it's a version of LambdaBot. The best IDE for Java, I have no idea, Barlock. I try to avoid writing Java whenever I can. So one could turn around and just build this map, shoving deltas in all the data constructors, and then the act of like accessing through them would push the deltas down into the other branch and the key and the value, so that by the time you inspected it, you would never actually know that there had been a delta there. The problem with that is it actually makes the constant costs much worse, because what you've done is you've pushed the costs, like you've multiplied them by 4. You have to push it into the key, the value, and the other branch when you were just going to be touching one branch. And so your costs do go up. And one of the nice things is that if I have that group structure that I was exploiting in order to make L instead of list earlier, if you recall, we started with list having a delta per data constructor, but L had a single delta, and we could just kind of mangle the entries as we were pushing them past. If we exploit that same group structure, we can make a more efficient map, which is what we'll do is whenever I go to insert an element way down here in the map, instead of pushing the deltas off the path so I have a path burned that has delta 0, what I'll do is I will leave the deltas intact along the path, but then like accumulate it and apply its inverse to the element before I go to push it in. So like if the path is going to push me 50 characters to the right, I'll push myself back 50 characters in order to compensate for the damage that would be done. So we can build a more efficient group relative map. And so that's what all this coda group relative crap is all about. How do I build maps and queues and catenable lists of located things, things with locations? I might have accidentally flipped you off. Sorry, Hodor. But that's the general idea of what all this group relative stuff is. And this notion of a semi-direct product turns out to be pretty key to making it all go. So here I have my relative classes packaged up in the backpacked module of, hey, look, if given a data type, can I relocate it by some delta? And there's a notion of a relative monoid, which we've already talked about, to Jason's cooking show analogy. And the notion of a relative order just gives me that less than or equal to, but I really want the strict relative order. I actually don't care about relative order at all. Strict relative order is where it's at. And then I build up a bunch of like coda algebra stuff on top of that. So now we have things like, once I have this notion of things that have deltas, like things I can measure, like I measure finger trees, and then I have ways that ORD interacts with delta, and rel interacts with delta, etc. And it starts becoming more and more crazy. What is a backpacked module? Yeah, so this has been sort of a recurring theme, I think, for this whole stream so far, since I got started, which is that I've been talking a lot about Backpack, which is a extension to Haskell, which was designed by Ed Yang. And what it is it's the addition of like almost ML-like modules to Haskell. And what you can do with them is, let's look at my unpacked containers library as an example. So in my unpacked containers library, we look at the Cabal file. There's this extra block here that says signatures. So there's a module named key, or a signature for something named key. And then I have a bunch of other modules that use this module signature. And so if I look at the key signature, this is just a module signature that says there is a data type named key, and it has an eq and an ord instance. Hello, Edward. Sorry for interrupting. For a relative beginner not knowing any functional programming, are there any immediate fast benefits to delving into it? I do think so. I think, like, playing around with Haskell for about a month or so is a good way to get a feel for just how little you actually need all the mutability that you're used to working with in your imperative code. One of the things when I first found Haskell, along the way I'd been like trying to build little toy languages that all looked like the bastard child of C and Perl and Python, because those were the things I knew, C++ and whatnot. And when I found Haskell, what I found was they had kind of better answers than I did for a lot of things that I'd been working on for like 10 or 15 years at that point. And it was almost embarrassing to me, like, that this stuff had been sitting there just out of my view that entire time. So, in some sense, like, I don't know necessarily if the rewards are going to be perfectly immediate for you, but I do think they're there. I guess one way I like to talk about it is to say there's a quote from John Carmack that I think is kind of informative. It's like he says something about what's the cost of using the wrong abstraction. You just don't know it, right? Like if you've been using the wrong tools your whole time, like if you've been like grabbing for a screwdriver and using it as a hammer, and you just don't realize that hammers exist, what is the cost of that? But then like that is a non-trivial cost. But then integrate that cost over the entire over your entire career. What's the cost of using the wrong abstraction for the rest of your adult life? So I do think it's worth it to dive into functional programming and understand what's there. Just because you're paying a cost and don't know it. What do I think about Kotlin? I don't think a lot about Kotlin because it doesn't really solve any. Like it's. I think of it as a worse Scala, and Scala is already off the bottom of my radar. I believe that backpack and stack don't work together. And backpack and stack. Okay, so what did we have? So we had an idea of here's a module signature of there's some data type key, I don't know what it is, and then what I did was I modified the code from data.set to just depend on key, and then I took the definition of set, removed the parameter a from it, and put key directly into the data type. But now what's interesting about Backpack is Backpack will allow me to unpack key, even though it doesn't know anything about it yet. And so this gets me a notion of a set that has fully unpacked keys directly into the nodes. And if you work out the performance of it, it's about 15 to 45% faster than data.set. In Coda, I use a lot of Backpack for different layers of abstraction. Because one of the things I find with Haskell code is a large Haskell code base tends to be like layers of an onion. Where you have like a small testable core, and then you start building things that depend on that testable core, but you have to like trust this core first. And it's very hard to mock out the previous layers without adding more and more type parameters that clutter up all of your code. And so what I do here is, let's look at an example maybe. So I might have like a notion of like whatever my tokens look like. And here we've got, I don't know, Coda, syntax token, Haskell. Here's like a pile of very peculiar, like some peculiar token type. And then earlier I mentioned the notion of a Dyke language, which is a thing that can be parsed by the bicyclic semigroup that we talked about way at the beginning of the stream before half the people joined. And what I want to say is, what do I actually need about token in order to build this other data type atop of it? These are the properties that I need it to have. I don't care what they are. So I could build another instance of this module signature and then mock that whole thing away. And then test all of this code, which is complicated in its own right, and it just goes on and on and on and on. And like some of this is some seriously non-trivial behavior. And I don't want to necessarily have all of the particulars about my token type cluttering up my testing of this code. And then, I don't know. I go off and then I build a lexer. So here's a lexer that is built with Alex. And this thing uses my Dyke language data type from earlier. But then I have a bunch of stuff that takes the lexer as given. And so this needs some notion of a lexer, which we just have a module signature for, some notion of a Dyke language for that token type that we had earlier, and builds like these ropes out of this stuff where I've got some particular choice of monoid. And the whole goal here is to have it so that when I'm done, if I look at rope or something like that, here, rope is a single concrete data type with no type parameters. Everything's kind of vanished. This looks like I had written completely monomorphic code, but it's still testable as if I'd left all those parameters to be expanded upon. So that's where I've been using Backpack mostly. It's for testing layers of code and for the ability to unpack things that I don't understand. I don't know what they're going to be yet. Those have been the two major use cases I've found. And like in the case that we're talking about here, I needed it in order to be able to talk about the notion of a monoid action without being incredibly dissatisfied with overlapping, messy, awful instances that tend to break users when they actually go to use it later. So having a particular class per data type that I want to be relative to and still be able to use Backpack to abstract over the monoid, I think is kind of adorable. Mind you, I find this kind of code very difficult to get back into. I find that Backpack's choice of using packages as the grain of abstraction is a little too coarse for me. It's really difficult to use in that sense. And we're just now getting to the point where it's going to become viable, really, to use Backpack in more Haskell code, as we've got a GSOC student this summer working on getting us the ability to have multiple public packages, multiple public libraries in a single Haskell package. Does the deriving mechanism in template Haskell solve similar problems? Template Haskell can solve a similar problem. You can use template Haskell to do a lot of the code generation that you get from Backpack. I think the difference is that Backpack gives you a type check story about that, so you can test your thing against the module signature before you go to look at the particular bits and pieces that are going to be generated by template Haskell. The driving mechanism, driving really only works for a single linear chain of classes. It's got its own problems. It's a different beast. I mean, for me, Backpack is sort of interesting in the sense that it's the first time that we've gained sort of the performance benefits of separate compilation for templates. And so it enables all of that almost partial template specialization like performance benefits for Haskell. So that's the performance side of it, but the debuggability side of it I find much better than the template story, because you don't have S fine, which is both good and bad. So let's see, what do we have left? Hello, Node Botanist and crew. So what do we have? We've now, so let's recap what we've managed to accomplish so far, because a number of people joined after the stream started. We started with what is the notion of a semigroup, a monoid, what's a group, what lies between a semigroup and a group. And so we found the notion of regular semigroups and inverse semigroups. We mucked around with Australian English to find something that was a regular semigroup that was not an inverse semigroup. We mucked around with parentheses to find an interesting inverse semigroup. We found like this weird, funny category structure hanging around on every one of our inverse semigroups, which was really a bit much. What else have we found so far today? We played with Australian English. We started playing around with this notion of monoid actions and monoids that act on monoids, or semigroups that act on semigroups. From there, we were able to figure out if the action was a monotonic function. We were able to build up our notion of, like, how would we deal with parse errors? How would we relocate parse errors? How would we relocate lists of parse errors and still maintain constant time? And still make it so that you can concatenate those lists in O1 time as well. So now we have O1 concatenable lists that can be relocated in O1 time. And this notion of a relative thing, for me, I kind of like the idea of, like, if you start applying this to syntax trees that you're getting out of the parser, you can have relative syntax trees. Here's a syntax tree that has only relative positions in it, so that when I glue it together with another syntax tree that comes from the same source file, I can shift things around. So I've got what is the interval of source text that this tree came out of, what is the interval of source text that this tree came out of, and here's how we glue them together and shift the positions around. And if we use like smart constructors in the access of this, like we were doing, or like I could do in Coda, in the Coda group relative map story here, we could build a smart data constructor for map. Like we just make a pattern for bin that says I take a size and a key and an A and a map KA and a map KA. Give you a map KA. As long as I have a strict relative order on K and A is relative. Wow, that is huge. There we go. So we could make a pattern bin thing that says, here's my size key value, left, right. And this builds bin. Or this goes the other way. Bin size key value left, right is equal to bin size delta is 0, key value left, right. And over here, we get a size, a delta, then we relocate by delta to get a key. We relocate by delta to get a value. We relocate by delta to get a left. So if you only used bin underscore and tip, you could never know that these deltas were lying around in your original syntax tree, or in this case, our map. Similarly, if you were to modify your syntax tree for your programming language to have deltas buried in all the nodes, but then only use smart constructors that don't see the deltas, only see the actual locations, then you wouldn't necessarily care that I'm relocating my syntax tree around. And I find that to be a really valuable pattern. And so this notion of using smart constructors to access my syntax trees, making the syntax trees relative so that I can relocate them constant time, that is starting to... That's resonated pretty well for me. But the notion of what monoid that I'm relocating by doesn't have to be a change of positions. It could be, here's a monoid of substitutions that I'm going to apply to my syntax tree. And then you can get an algebra of explicit substitutions. But then have smart constructors that hide it from you. Ugh. All right. I am actually starting to wind down here. A, my throat is going. And B, I've kind of run out of things that I really want to say today that kind of dovetail nicely with what we've said so far. No explicit implementation in 197. Let me go down there. Oh, this is the wrong thing. Backpack is cool, but what about quantified constraints? I talked a lot about quantified constraints last time. I don't need them for anything in this particular problem domain. And yes, Manip, we have a whole pile of... Oh, that's right, you did want to go through quantified constraints and if there was a nicer way to deal with the Patterson conditions. I think we're not going to get to that this time. When's my next live coding happening? Probably do it again next Sunday. I'll definitely send out an announcement a couple of days in advance. I'm trying to get back onto a regular cadence, and I don't have anything that I know of that's going to keep me from streaming on Sunday. But I am traveling to New York during the week next week, so I might have, if something weird happens there and I have to stick around longer, I might not be able to make it back. But my intention is, like 80%, I'll be streaming next Sunday. I'm trying to get back onto this streaming every Sunday kick, which was my original goal.